Okay, we're recording. Looks like it's going right. Okay, so here's where we were last time. We were talking about this kind of weird idea of an oriented density. You may remember I kind of referenced this back in chapter 6, I guess it was, and pointed out the gradient is what you might call an oriented density. Because after all, if you look at what it does, it's what you might say it's what you vector multiply by vector size to get stuff, right? So it's kind of a stuff per unit, size in a vector sense of the word, kind of you might say, if you are willing to be flexible in this sense. Okay. All right, so in the same way, you can think of curl as also playing that role. Again, notice that this is a vector notion of size, ds, that you in a vector sense, namely dot product sense, you multiply by this curl to get, again, stuff. Right? So it's kind of a vector notion of a density, and I like the word oriented, but it'd be different terminology you could use. Okay. All right, so in the same way, no surprise then that curl, when you break it down to its direction and its magnitude, the direction is the direction that the changing, that the increasing is happening in. At least that's the direction it's primarily happening in. In any other direction, you're just kind of piggybacking off of the change that's happening in that direction. Right? If you walk uphill, that's the direction of uphill. If you walk slightly off of uphill, yes, you are still going to be noticing that you're going to be going up as well, right? But because of the extent to which you are going in the direction that change is actually happening, and the magnitude gives you the amount. So likewise, you come down here, and now I'm going to zoom in. Same deal with curl. Curl has a direction and a magnitude. The direction is telling you the direction of what I'm going to call the rotation, right? Around what axis is the rotation happening. And then the magnitude is telling you how much around that axis, how much rotation is happening. And again, we're not going to get into units and that kind of thing, but more means, bigger means more and smaller means less. And the units are somebody else's problem, as I like to say. Okay. All right. So that was where we ended it pretty much. On the next page here, all I had done is really kind of drawn a picture of that. But again, then here is our curl vector, and that is telling us by way of the direction that vector points, that tells us the axis that the fluid's rotation is going around. And by its magnitude, it's giving us some sort of an indication of how much of a tornado is that. Is that a very strong tornado with a lot of rotation of fluid, or is it this kind of gentle, kind of, much less rotation? So, okay, now, next question I want to address, and this is just going to be a hand-waving thing, with the idea that curl is, like I described here. Do we buy it, I'll say, that curl, when you dot with the normal vector of the piece of surface, that in some sense is going to get your hands on the extent to which the rotation that's happening around your axis, right? The extent to which it's also kind of sort of happening around whatever boundary of whatever piece of surface you're looking at, right? So in the same way that dot product with the direction you're going tells you how much of the steepness of the mountain are you personally going to experience, right? In the same way, does this dot product kind of do the same thing? And so here's a picture that I have that I think gets right at that pretty well. Now, again, this is not a proof. This is not a derivation. This is just I can kind of see how that kind of works kind of thing. That's our goal. We are interested in why the dot product of the curl and the normal vector to our piece of surface. Why does that dot product relate to how the circulation of the fluid is tracking the direction of the boundary of that piece of surface? And I'm going to say appeal by picture. Notice that it is kind of because this circulation is kind of, if you will, loosely speaking, going around in the same direction that that boundary is. That's why these two normal vectors, that's why these two vectors here are pointing kind of in the same direction. Right? It's just, again, just appeal to the picture. When the boundaries movement around the boundary is going around in exactly the same way, around exactly the same axis as the circulation of the fluid itself, then those two vectors are pointing in the same direction. And by contrast, if you were to look at a situation where the curl is like this, in other words, the axis of the rotation is that way, we've got a fluid going around, kind of like so. But if the normal vector is like that, not pointing in the same direction, the dot product would suggest, and if you look at how these that dot product's going to be small or zero, right? Well, again, that tracks pretty well, as it should, with the fact that the circulation of the fluid is entirely different direction from the circulation, or I guess I should say your movement as you go around the boundary. And to the extent that it's actually kind of hard to hand gesture this, you can try it for fun if you like, but the fluid is going around like that, right? And then the boundary is it is, again, harder than it looks, right? But this kind of rotation around that boundary curve and that kind of a rotation of the fluid, they're in different directions. To what extent is that fluid flowing along that boundary curve? It's not to speak of, right? So, in the same way that this dot product is small, likewise, the circulation of that fluid around that boundary, also small. So now again, this is just hand waving. It doesn't prove anything, right? But I hope this is at least makes it sound plausible that this expression, let me not get ahead of myself here, that this expression is kind of a measurement of the extent to which the circulation that's happening is in fact happening around the piece of surface you're looking at. And thus that this should be circulation density. It's kind of, again, plausibility argument only. Okay. Alrighty. A couple of physical examples. This first one is just piggybacking off of an idea we've already talked about. So we've talked about this two-dimensional version of this story, and that is that the two-dimensional thing called curl is a way of getting your hands on the idea of to what extent does I shouldn't use the same color there. To what extent does the motion of the fluid, right, if you're looking at a fluid F, to what extent does that motion of the fluid make some little floating object, in this case I'm looking at a leaf, to what extent does it make the floating object turn as it flows downstream? Right? And I think this is pretty believable. Again, what is a leaf doesn't have enough inertia to kind of do its own thing. If the water moves, the leaf moves. The leaf does what the water tells it to. And so to the extent that the curl is a measurement of rotation in the fluid, well, likewise, it's going to tell you, in some sense, the rotation of the leaf. That's the idea. So analogously, now if I try to make a three-dimensional version of this, now we're in 3 dimensions. Again, I'm going to have the fluid representing, the velocity of the fluid be represented by the vector field. So again, to whatever extent, there may be some extent to which the fluid itself, right, is rotating. How do we get our hands on the extent to which a fluid is rotating? Well, that's curl. That's what curl does, right? Curl tells us the axis of the rotation, and it tells us in some sense by its magnitude how much rotation there is. So if I had some floating balloon, now I've got to make a different physical metaphor here because it's three-dimensional now, right? This is not something floating on the surface, two-dimensional surface of a river. Now I have something moving around in three-dimensional space through a three-dimensional fluid, maybe air, right? So a perfectly balanced balloon, just exactly the right number of days after the party, and it's no longer stuck up on the ceiling, and it's just kind of floating weightlessly around the room, right? Well, to the extent that the air is rotating, the balloon likewise is going to be rotating in the same way. And Curl is going to tell you the axis of the rotation and, again, units aside, to some extent, the magnitude, how much rotation. Everybody buy it? Everybody see how it's the same idea as Curl, as two-dimensional Curl? Analogous? All right. Here's another one. Now, this one is arguably more important for engineers in the sense that, the reason you need to understand this example is because this physical example helps you understand the math. Here, the math is going to help you understand the physics. And the engineers among you will need to understand this. So here's a fact of physics. By the way, be sure not to ask why this is. This just is. It's empirical. You can relate this to other things and call that an explanation, but deep down, ultimately, why does the universe behave this way? Nobody knows. We've just noticed that this seems to be what happens, right? Why is gravity downward? I'm glad it is, but I don't know why it is. It just is, right? So same thing here. All right, so I'm going to talk about what's called a flow of charged particles represented by a vector field that we call a current field. Now, I imagine you all have probably heard of current before. Current in a wire addresses the matter of, well, as charged particles move down the wire, how many charged particles per unit time are moving past some reference point on the wire? Yeah. Okay. Well, a current field is basically the same idea. It's just addressing the fact that not all flows of charged particles are confined to metal wires, right? That's we use them a lot like that, but there can be movements of charged particles around in any way. So here's the fact of physics, and I think this is surprising. It's certainly not expected anyway. This is a weird fact of physics, but when you have a flow of charged particles, that creates a magnetic field. And the magnetic field is kind of like that. And there's a right-hand rule and everything. Thumb in the direction of the current field, and the fingers of your right hand point in the direction that the magnetic field points, and stuff like that. All right. So now again, don't worry about why. That's just empirical. That's what is. So what's the relationship? What's the algebraic relationship between these two things? And it turns out to be very conveniently just this right here. That the curl of the magnetic field, let's see here, let me do my color coding. Yeah. The curl of the magnetic field is, other than a constant there, is the current field. You can even kind of see it in the picture, right? I mean, the current is pointing in the direction that the magnetic field is kind of, if you will, flowing around. Now, of course, magnetic fields don't represent the flow of particles. So it's not really flowing, but it is represented by a vector field that, if it were representing a fluid, would be kind of circulating. Okay. All right, now, how do we know this? Where does this come from? And you're going to notice already, I'm sure, whoopsie. Did my stylus already die? I haven't been, oh my gosh, I've been going for 15 minutes and this thing's already dead. Let me plug it in, sorry. Okay. The way we know, the way we know this is, let's clean up the mess. You can, again, empirically measure certain things. And this one here is something you can totally measure, right? You can just detect the strength of the magnetic field. You know what the current is, and blah, 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 and you can compute directly from empirically observed data that the circulation of the magnetic field is whatever. Right? It's, again, you can measure it. You know what the current is. Again, that could be measured or controlled. And you just notice that, yeah, they are always in proportion like this. And once you empirically notice that, then you can also recall that aside from this constant in here, that's just, of course, a multiplicative constant, not interesting, current is literally the flux of the current field. That's kind of the definition of the current field. The current field, J, is a vector field representing the flow of a fluid. Flux of a vector field representing the flow of a fluid is what tells you how much of that fluid per unit time. That is current. Right? So this equation down here, again, pretty direct. And then likewise, you probably noticed the pattern here. I've just recopied Stokes' theorem. Circulation is a vector surface integral of the curl. Write down Stokes' theorem, and that results in us then having these two integrals being equal, and that means their integrands have to be equal because they are equal over all possible surfaces. Excuse me. And that then gives us another one of Maxwell's equations. Differential form, and again, the other version over here, this over here is what we call the integral form of the same equation. We can, again, consider them kind of the same equation because these two facts are, you might say, global versus local takes on basically the same phenomenon, or you might make the same observation we did when we were talking about gravity and electric fields, that they are immediately and directly connected by one of our big theorems, in this case Stokes' theorem. Right? And I think it is a healthy exercise to notice how much, just on the page, how much, and I did this on purpose, but how much this argument and little connection of quantities structurally identical to when we were talking about electric fields. And that's it's eyebrow raising, and it's something to think about. All right. And when you take an E&M class, these are going to be really, really useful ideas. Okay. All right. Moving along. Y'all remember this one. Everything up on the screen here is already been discussed. This is old news. We were talking about path independence, and we made the observation that all gradients are path independent and vice versa, and you can rewrite path independence by saying circulations are all zero. That's just the different phrasing of the same thing. Everything in green here is just about path independence. And we also had this observation that these two equations are kind of morally the same, as long as we're talking about continuous integrands, which we are here. These are kind of the same because, look, if you have some integrand that makes all integrals zero, no matter what domain you look at, how could this be? There's an integrand that makes all integrals zero for every domain. There's only one way to do that, and that is that integrand itself must be zero. Right? So we talked about all of this, and the thing that connects them was Green's theorem. Green's theorem specifically tells you that circulations can be computed as double integrals of curl. Right, so that's what sort of connects the left side to the right side, and therefore that's sort of the final piece of the puzzle that tells you how the local test works. So why is it that curl being 0 means you're looking at a gradient of something? Well, that's the final piece of the puzzle. So I then stated this. I stated that in 3 dimensions now, that it's curl still, the thing we still call curl, but we use a different notation, right? But anyway, again, curl is the thing that it plays this role of being a local test. Namely, it's the thing, let's see here. This is the thing which, if 0, tells you that you are indeed looking at a gradient. Just in 3 dimensions now instead of 2. And I made this statement, and we computed with an example and just kind of took it on faith that our example must be right. But I didn't ever give you a justification for it. And so what I said at the time was that the way you complete this argument for the 3-dimensional case is morally equivalent to what we just did up here for the 2-dimensional case. The only difference is we didn't have the necessary theorem at that time. And now we do. So we're going to fill in this little blank. And let's see here. Let me, I guess I better do about like this. We can fit all this onto, whoop, not quite. Fit all this onto the screen. There we go. So in the same way that we'd already had these different formulations of path independence, and in the same way that if an integral is 0 for every domain, then the integrand must be 0. Well, likewise here, same argument. It's just that now it's a flux that's always 0 for every surface, and therefore the vector field must be 0. Still, same basic idea. And in the same way that Green's theorem, by connecting those, connects the dots here. Likewise, notice what it is that we need in order to connect that to that. Well, it's Stokes' theorem. It's exactly Stokes' theorem. Stokes' theorem literally says that circulations, right, can be computed as fluxes of curl. So that's the missing piece. That's what allows us to draw this same connection. That's what allows us to finally understand why that 3-dimensional local test works. And again, I'm a big believer in analogies, right? I think there's a tremendous amount of value when you see that a more complex and sophisticated argument like this down here is morally, structurally the same as this, kind of more relatable, perhaps, argument in 2 dimensions up here. Seeing how they're really kind of the same argument, I think makes it a little bit easier to kind of put the pieces together. But anyway, I like to point these out when they come up. All right. So, moving along, let's see how are we doing with the good stylus. It's back in business. Okay. Let's see here. So here's a new idea, kinda, called surface independence. By the way, this is not in the book. I think that's weird. I think surface independence is one of the most underappreciated ideas in multivariable calculus. Most multivariable calculus textbooks that I've seen don't talk about it. I don't get it. Now you're about to see why. Here is the analogy. I'm going to loosely say it's just like path independence. It's really just like path independence. I'm going to leave both of these visible at the same time here so you can kind of cheat and look down and see the analogy that's about to happen as I go through and remind you how the old business works. And so the old business was path independence. If you have a curve over which you're interested in computing an integral, And if you have another curve over which you're interested in computing an integral of the same vector field, f, we say that's path independent if whenever the curves start and end at the same point, those integrals must always be equal. So this is the special property that path-independent vector fields have. Path-independent vector fields, anytime you have two curves with the same start and the same end, they'll always give you the same vector line integral. So everybody remembers this? Okay. All right, well, here's the analogous idea when we're talking about three dimensions and surfaces. So we're going to be looking again at two separate things. It's just that now they are surfaces instead of curves. These surfaces are oriented by their normal vectors, not their tangent vectors. Not the direction you're going along them, but the direction you're going through them. Right? So geometrically different. And sometimes those two surfaces might have the same boundary, but wait a second, these aren't boundary points. These are, well, we're talking about surfaces, so their boundaries are curves. Right? So you might have two surfaces with the same boundary curve. We're going to ask, is there a relationship between, not the line integrals, what line is there? But we're going to look for relationships between the fluxes instead of the line integrals. Everybody see how this is setting up analogously? I mean, obviously, it's different. Right? It's geometrically different. It's sort of one dimension higher. It's in 3 space instead of potentially as little as 2 space. It's 2-dimensional surfaces instead of 1-dimensional curves. They have 1-dimensional boundary curves instead of 0-dimensional boundary points. All the same kind of ideas, just 1 dimension less. Or now 1 dimension more. So sometimes a vector field has the feature that in such a scenario you always get the same flux. And if a vector field is surface independent, we call it, those two fluxes will always have the same path. And again, this is a special property of a vector field. Most vector fields are not surface independent. Right? This is not a new fact that will help you compute any flux you might need to compute. This is only for these special cases of surface-independent vector fields. And again, it's a very surprising property. It's a little bit weird that this happens at all. Right? In the same way that path independence was pretty weird. Okay, let's see here. We had this alternative formulation of path independence. The alternative formulation came by looking at sort of following C1 and then going backwards along C2 and realizing that means that we're going to compute the C1 integral and the C2 integral, but we're going to have a minus sign on the C2 integral. And of course, if C1 integral and C2 integral are the same, that means their difference is going to be 0. So we have this alternative formulation of path independence. And I'll bet you can see this coming. We also, likewise, can talk about an analogous argument, analogous construction. Over here, if I look at the surface that's made up of S1 and S2, oriented the same way that S1 is, which you'll notice means it's oriented opposite of the way S2 is. Right? Same deal. So along C1 means opposite C2. Then the alternative formulation is that those closed fluxes must be 0. Okay, so extremely analogous ideas. All right. Okay, now y'all may recall when I first showed you path independence, I presented it as this implausible. Come on, how could this ever be, sort of a thing. And then I showed you that not only is there an example of such a vector field, an entire category, all gradients were path independent. And it immediately follows from the fundamental theorem of line integrals. Okay, well, here's the analogous argument here. I claim that all curls are surface independent. How do I know? Okay, well, the test, I need to know that whenever I have two surfaces, S1 and S2, as long as those two surfaces have the same boundary curves, right? I need to know that this green flux and this blue flux are always the same. How would I possibly relate the flux through that upper green surface to the flux through this lower light blue surface? They're different surfaces. They're almost entirely covering different points. Seems weird, right? But notice when it comes to computing this integral here, let's see here. So f, by assumption, is a curl. That means that this integral right here is a flux of a curl. Flux of a curl. Where have we heard that phrase before? Flux of a curl. Flux of a curl is one side of Stokes' theorem. So you can compute flux of a curl with a line integral around the boundary. And okay, now let's look at the other side. Let's look at this thing right here. We've got this flux right there. Oh, wait a minute. That is a flux of a curl. Likewise. So we can compute that by way of Stokes' theorem with a line integral around the boundary. And therefore, the green integral and the blue integral are computed with the same other thing, and therefore they're equal to each other. So, surface independent. Everybody see how that works? It's a clever argument. Very analogous to what we saw with path independence and gradients in the fundamental theorem. Okay. All right. And by the way, it does go the other way as well. This one is harder to see. There isn't, I can't give you a sketch of this proof. This is just a harder fact. But conveniently, it's true. Again, restricted category, nice vector, no discontinuities, no singularities, nothing bad's allowed to happen. But for nice, sufficiently nice objects in question, this is also true. Okay. Alrighty. So we have a new set of ideas to talk about. We just got through establishing these things right here, right? Being a curl means surface independent, and vice versa. And furthermore, surface independent can be rephrased in terms of closed vector surface integrals, all being zero. So we've just established that these three things are all the same. And you can probably guess what I'm about to do here. I'm going to say, okay, well, these two statements, again, are obviously equal if all triple integrals over all domains are all zero. Come on, that integrand's got to be zero. And how can I relate these green statements to those blue statements? Can I relate closed, namely boundary fluxes, to triple integrals of divergence? Why, yes, we can. Gauss's divergence theorem does that. So again, I get a convenient local test. And if you find yourself at some point in the future wanting to know, hey, I've got some vector field and I would like to know, is my vector field surface independent? Namely, is it a curl? How do you tell if your vector field is surface independent? Oh, okay, yeah, you could compute the divergence, see if you get zero. If you get zero, then yes, indeed, it's surface independent. Okay. All right, now that's a lot of ideas. I just threw a whole bunch of geometry at y'all, right? I just threw a whole bunch of complex sort of constructions and relationships. I assume that y'all did not 100% get all of that. Right? I assume. And that's fine, right? So I want to remind you, okay, especially at this point in the course when the ideas are pretty challenging, right? Pretty substantial. The way that you digest these ideas is not it's not just going to automatically happen, just boom, right there in class, right? What you have to do is give yourself time to kind of chew on it, right? And so that's one of the big benefits of these lectures being recorded. I encourage y'all to go back and re-listen to this page of notes, right? To whatever extent might be necessary. If you don't need it, that's cool, right? But if you did not maybe quite catch all of this, then listen to it again. Use the pause button liberally. Pause, think about it, write some things down, flip back in the notes, remind yourself how whatever such and such works, right? Give yourself the time as necessary. That's kind of what I'm expecting you're going to need to do for substantial ideas like this. Okay. All right, let me show you how it all comes together and how we can use this to solve problems. So here we go. We want to compute, let's see here, computing a flux. Surface is given. Vector field given. How are you going to compute this? I'll remind you. Tools in the toolbox. Don't just grab the first tool you see. Right? Think about your options. I suppose I could parameterize that surface. Not even that bad. I can definitely pull back through that parameterization. That would just give me a great big gigantic double integral, and that's kind of doable. Right? It's going to be a pain, but it's kind of doable. But here's the much better way to do this. Let's just see, just in case. Might I be able to use surface independence here? After all, look, surface independence is arguably kind of a computational technique because, just like with path independence, if you know that your vector field is surface independent, you know that any flux that you've been asked to compute, whatever surface that might be, all you've got to do is dream up some other surface and compute that one, just so long as they have the same boundary curve. Any other surface with the same boundary curve, whatever. Any surface you like. As long as it got the same boundary curve, if you know you have a surface-independent vector field, you can just trade and say phooey on that original surface. I don't like it. I like the blue surface better. And then go for it. Okay, so that's what we're going to hope works out here, right? That is a tool for computing fluxes. I'm being asked to compute a flux. Let's see if this works. We're going to use our local test. We're going to compute divergence, right? Compute divergence. We're going to see if we get 0. If we do, we're going to declare surface independence and then take it from there. So you compute this divergence, and y'all know the formula for divergence, and chugga, and boop, yep, 0, therefore surface independent. I've just discovered a massively powerful option on the table, right? For compute this integral that I've been asked to compute, I can change the surface however I like, as long as I don't move the boundary. Everybody see see how that's awesome? Okay, so let's think it through carefully now. I do have to be careful not to move the boundary, not to change the boundary at all. So here is our original surface. Let's see here. It's all of this business right there. Oriented downward, by the way. Let me go ahead and indicate that. Okay. If I'm going to dream up a new surface that has the same boundary, I'd better first understand the boundary. Okay, so the boundary of this surface is this curve right here. Now, part of that is just geometry. Part of that is just the matter of realizing, look, I've got an upside-down paraboloid. Only the part of that paraboloid that's above the xy plane that doesn't sort of extend infinitely downward. This is sort of an upside-down bowl, right? The boundary of that upside-down bowl is the lip of the bowl, which is right there. You do have to think carefully about the orientation. That's this business with the thumb and the right hand, thumb, and you look at the fingers. That defines a swirl, and you see how it side swipes. So this is a little bit of a geometry challenge. Let's just think this one through. Do about like this. And now I'm going to get rid of all the distractions there. I know that whatever point I am... Whoa. I wanted to be in pencil mode. Whatever point I'm at, downward is my orientation. And notice that you're going to be tempted to call that inward. Which, yeah, okay. It's, again, not particularly confusing. It's people know what you mean. Okay, so I am now then going to imagine such a point, but I'm going to look at one that's like here, again, near the boundary. Which direction does that normal vector point? Well, it points inward, if you will. So you got to kind of use your imagination there. It's a two-dimensional screen, right? But imagine that pointing inward, and now we've got and it is very helpful to do this three-dimensionally. And by the way, you're perfectly welcome to make any, all of these hand gestures that you might find useful during the exam. Go crazy, it's all good. So here, if the thumb, right, is pointing into the screen, right hand, look at your fingers, and now you see which way the swirl is going to go. Right? And I think that swirl is going to go what I'm going to call clockwise, as seen from where we're looking. Right. So inward, thumb, right hand, fingers, clockwise. So let me draw that clockwise swirl. Get back over here. So the clockwise swirl, like that on the surface. And how does that side swipe up against the boundary? Well, it side swipes in that direction. Everybody buy it? Okay. Now here's a fun exercise, something that I encourage everybody to do this sort of on your own, but think now instead about a different point, maybe on the back side. Imagine a point, sort of in the far away, the backside of this thing, and then its normal vector is going to be kind of coming at us. And then think about what that means, about which direction the swirl goes, and persuade yourself that you get this, which of course is the same orientation on the boundary. But it's a good little exercise to think it through, so something to do. Okay, is everybody all right? Okay, so here's our boundary. Let me get rid of all of this. We've got our boundary curve, and let's see here. Let me do it in the right color here. Here's the boundary curve, and it's oriented like this. And that came to me from, came to us from this surface. But I don't have any further use for that surface. I'm going to pick a brand new surface because that one's all curvy and complicated stuff, and I don't need that. I don't want that, right? We now have the right. We've already established that this is a surface-independent vector field. We get to pick any surface we want as long as its boundary is that same curve there. So phooey on that thing. And what is your favorite surface that has this dark blue curve as its boundary? And I'm going to go with this one right here. I think that's a pretty easy pitch. That's a much nicer surface. In fact, it's flat. It's awesome. The formula for that surface, yeah, it's real easy. Z equals 0. It's right there in the XY plane. The normal vector is easy to write down. The normal vector is just straight down. And again, you have to play the right hand game. You have to think about which direction, consider both possibilities, right? And downward is the one that is going to make the swirl going in the direction that it should be going. So there's your normal vector. All right, how are we doing? Is everybody with me so far? Okay, so we've made lots of progress here. We were asked to compute an integral. We found that this is a surface-independent vector field, and so because it's surface-independent, I'm going to compute this different flux instead. Just as good, right? Oh yeah, go ahead.
I don't quite understand how you're getting the normal you draw for S from saying S is oriented downward.
Yeah, that's right. So, okay, yeah, let me talk about that. So, the language about orientations is sloppy. Okay. It has to be. Because if you think about what an orientation really is, right, an orientation is not just a single direction, it's a bunch of different directions depending on where you're looking. Right? So how would I describe all of those directions all at the same time? I guess I could write the formula. I don't want to have to write the whole formula, right? I want a convenient way to deal with this. The good news is all I really need to do is distinguish these directions from the alternative. The alternative is this. So I don't need to describe the blue vectors exactly. I just need to distinguish the blue vectors from the green vectors. And what you notice is that all the green vectors point at least somewhat upward. All of the blue vectors point at least somewhat downward. It's not perfect to call either of them downward, but if I say downward, no one's picking the green. You know what I mean? Yeah. So that's how we use language to describe orientations. It's, look at your two options. Try to find out what distinguishing characteristic is it that perfectly separates them from each other, and then just use that language.
Okay.
Yeah. So that's all we're doing. It is a weird idea to kind of get your hands on. So just summarizing again, we were looking at this integral over that surface. We established surface independence, which means I'm allowed now to pick any surface I like that has the same boundary. And here it is. I'm going to pick that surface right there. It's got the same boundary. I'm going to compute that integral instead, hoping that it's going to be an easier integral. And in fact, it's super easy because you can, let's see, now getting rid of all this green stuff that we don't need anymore. We've agreed that our normal vector here is downward, and thus, and now here when I say downward, I'm talking about on our new surface. On our new surface, downward is literally straight down. So it's, in this case, literally 0, 0, -1. And the vector field that I was supposed to be doing this with, that vector field, that dot product is super easy to compute. That dot product is just minus xy. And you see all that remains then is I'm computing now I'm computing an integral on that surface. By the way, a scalar surface integral. Now on that, so I've already done the dot product, so it's a scalar surface integral, and I have an integrand that I am highly suspicious has some nice symmetries, and I'm going to let y'all think this through, but this, bad color choice, not green, this integral is 0 by symmetry. Details for y'all to think through. Make sure you're super comfortable with all the details necessary to make a full argument there that this is 0 by symmetry. A lot of little details to think through. Make sure you're good at that. Reminder though, on the exam, you don't have to provide those details on the exam. If you make a symmetry argument, you just need to say equals 0 by symmetry. You then have to tell me what line or plane you're making the argument through, and you have to be right. Little minor detail there. Okay. All right. Is everybody happy? Okay. So this is a really nice computational method. Now let's talk about the underappreciation of path independence. Surface independence. Path independence is highly appreciated. It gets discussed in every multivariable calculus book I've ever seen. I am all for it. It should be. It's an important idea. But as a computational tool, I mean, if it's path independent, then it's a gradient. We know how to find anti-gradients. We could just use the fundamental theorem of line integrals. So do we really need that? I mean, it's nice to have backup tools, I suppose, and sometimes it's really useful. So why can't we make the same argument here? If it's surface independent, after all, let's see here, let me clean up this. If it's surface independent, that means it's a curl. Why don't we just compute that anti-curl? Have you noticed I never showed you how to compute anti-curls? That's because it's hard. And there isn't really, that's not something that you can, there is no convenient little algorithm that you can just kind of do that. It's tricky. It's not something that we're going to be able to do in this class. So yes, technically, while it is true that any time you could have used surface independence, I guess technically, yeah, you could find the anti-curl and use Stokes' theorem, but we don't know how to do that. So in situations where you need to use surface independence, it's your only tool in that direction. So that makes it a more valuable tool. And again, just for silly analogy purposes, if you already have a toolbox full of hammers, someone comes to you and offers you another hammer. Okay, I guess, yeah, sure. It's a slightly different hammer, you say? Okay, I guess it might be useful, right? But that's if you already had other hammers. If you have no screwdrivers in your toolbox, and someone offers you a screwdriver, you got it. Oh, that's a big deal. That's a big get, right? It is the only tool that actually, in practical purposes, works for computation. That's a good one to know about. So, from a computational point of view, I maintain that surface independence is more useful than path independence, and yet path independence is all anyone ever talks about. I just think that's strange. Anyway, all right. Okay. So, all right. So we're basically done with the material for the course. Sorry, we haven't done chapter 4 yet. We're basically done with the material. Sorry, little matter of an entire chapter in the book. But we're basically done with the chapter 7 material. Now, I do have some stuff in here about this diagram business, and this is not so much new material as a way of organizing the tools that I've already given you. And I think it's very, very valuable. I am a huge fan of this point of view. I think this also is underappreciated. So I'm going to have this conversation with you. I'm going to do this, though, on this representation of this diagram. This diagram, just as a reminder, is a rip-off of very sophisticated tools that were created not that long ago that do sophisticated and powerful things that are well beyond what we're going to talk about in this course. But even though we can't talk about them formally, we can kind of notice and capitalize on the many patterns and free information that you get basically for free if you just organize the ideas and the objects as suggested by this diagram. So anyway, let me walk through some of those. You'll recognize part of this. This business up here, back in chapter 3, I said that amazing things happen if you just take gradient and curl and divergence. If you just put them in that order, you compose them. The Legos fit together. If you compose in that specific order, this is highly non-negotiable. Gradient, then curl, then divergence. then really nice things happen. And we talked about the lifetime business, right? So if you have something here, you take its curl, you get something there, you take the divergence, you will get 0. And likewise, if you have some vector field, if you compute the divergence and you get 0, then that vector field must be the curl of something else, as we just discussed. Right? So, not new ideas, but it's a pattern. And so this, again, when you put the operators together in this order, it's really nice that you don't need to memorize like 6 or 8 separate statements. You really just need to understand this idea that everything has a lifetime of 2. That's like 8 theorems. So let's see here. The one counterexample is if you have a constant, its gradient is 0, and that's the sad little story. That is the counterexample. That's it. So that's just got to be thrown in there. Okay. But let's face it, if you're looking at a function that's constant, you don't need sophisticated tools. Constants are pretty easy to deal with, so don't worry about it. Okay. All right. Now, we've talked about in the two-dimensional case, I made the observation that if you think of the fundamental theorem as saying we've got a curve with boundary points and a function with a gradient field, and if you evaluate like so, then you get the same thing on both sides. And then I pointed out that that pattern is the same pattern that describes Green's theorem. Okay? That's pretty cool. Totally different geometry, completely different participants, different operator, different types of objects. Same pattern. Right? So that's pretty neato. And all of that works down here just as well. So in particular, why am I not zoomed in all the way? Let me do it like this. The fundamental theorem of line integrals, again, that evaluate this way, evaluate that way, you get the same thing. And the nice little exercise, I want to encourage you all to think through the details on that. But that is exactly the pattern that describes the divergence theorem. That's exactly the pattern that describes Stokes' curl theorem. It's the same pattern. And when you notice, this can't be coincidence, right? So when you see something that can't be a coincidence, what that means is this pattern holds for an underlying reason, and that underlying reason is sophisticated theorems that we're not able to discuss. But the point is, yes, there is a single theorem that unifies all of these theorems. All 3 of these theorems are just special cases of a single, larger, more powerful theorem that, again, we're not going to understand. So why does that matter? It doesn't matter that you know the more advanced theorem. You're not going to know it. That's okay. What matters is to notice that that pattern is there. Right, and then capitalize on the fact that pattern is there. So you don't have to memorize. By the way, I'm going to confess in all of my dealings with these theorems, which have been many, right? Math guy, right? So no surprise, right? I'm going to do a lot of this kind of stuff. But also physics uses these theorems tremendously. A lot of physics uses this kind of stuff, right? And I did a physics major too, so I've clocked a lot of hours with these theorems, and I've never memorized the theorems. I memorized the pattern, and I encourage you to do the same, right? Once you remember that the operators go in that order, then once you've accepted this idea that this is the pattern, right, then you just memorize 3 theorems. It's that same pattern applied in these 3 different contexts of this diagram, organized in this very special way. And again, you gotta organize them in this exact special way. Okay, so neat fact. Okay, here is the last thing I'm going to tell you real quick, and then we're going to do some examples. So you'll recall that I talked about back in 2 dimensions that there are special vector fields. The special vector fields are the ones for which Green's operator gives you 0, namely they are irrotational. They are the ones that are gradients of some function, namely they are gradients. They are the ones where if you take 2 curves with the same boundary points, you'll always get the same value for the line integral. That's path independence. Right? And these special vector fields are the ones that have these 3 properties, and any conveniently, as long as there's no singularities, discontinuities, nothing bad, any vector field that has any one of these properties has the other 2. They're always simultaneous. Right? That's pretty awesome. Okay, so now just another reminder while we're on it. How did we relate Green's operator being 0 to path independence? Well, Green's theorem was the tool that allowed us to make that connection. How did we relate path independence to being a gradient? Well, the fundamental theorem of line integrals is what allowed us to make that connection. Now that's just summarizing. That's just I'm just representing on the diagram here, sort of I don't know what, about 10 pages of lecture notes or so. But we made a bunch of arguments that basically represent on the diagram like so. Here's where it gets interesting. That same pattern works down here. Let me go down here. Now oh gosh, can I do this? Okay, good enough. So same pattern works down here. There are special vector fields. Special vector fields for which curl is 0. That are gradients of something else. That are path independent. And it was Stokes' theorem that allowed us to make one of those connections, and it was the fundamental theorem of line integrals that allowed us to make the 3-dimensional fundamental theorem of line integrals allowed us to make the other connection. And you might say to yourself, okay, well, yeah, sure. I mean, it's all the same operators. It's gradient. It's curl. It's vector line integrals. That's not that surprising. So here's where I think it gets really sort of like, you got to be kidding me. The exact same pattern holds over here. It's the exact same pattern. Bonkers. So again, you don't have to memorize a whole new slew of ideas. You just have to remember that the pattern is the same. Right? So there are special vector fields. Special vector fields whose divergence are 0. Those are curls of something else. Not that we know how to find that. They are surface independent. We made this connection here by way of Stokes' theorem. Just look back in the notes, right? We did that earlier today. And we made this connection by way of Gauss's theorem. And again, we did that just earlier today. So this just absolutely blows my mind that the pattern that makes sense over here, exact same pattern, also works over there. So again, what's the upshot to y'all? The upshot to y'all is, to whatever extent you feel like you understand path independence, just kind of slide everything over one notch in the diagram, and that will point right at exactly what the analogous idea is for surface independence. Really helpful pattern. Everybody okay? All right. Okay, let's do some examples. so here is how, roughly speaking, how we're going to compute line integrals and surface integrals. By the way, we're not going to get through all of this today. I never do. In fact, I rarely do, I should say. So in past semesters, I have, there are 6 examples here. These 6 examples are all kind of supplemental, kind of helping you think through how to use the diagram. I have, in cases when I didn't get through them, I've recorded supplemental recordings that, I encourage y'all to watch. And we're going to get through as much as we can here, but I encourage you to watch the recordings for the others. And I'll put them up on the YouTube channel as usual. Assuming I remember, please don't let me forget. If I forget, please remind me. Anyway. Okay, so step 1, when you're going to compute one of these integrals, if you've been asked to compute a line integral or a surface integral, first, identify your context. Where are we? What kind of an integral have we been asked to compute? First of all, was it in 2 dimensions or 3 dimensions? Pay attention, notice, right? So, for example, down here you see my vector field has 3 coordinates. You see my parameterization has 3 coordinates. I'm pretty clearly in 3 dimensions here. And furthermore, I've been asked to compute a line integral in 3 dimensions. So we're going to pop over to our diagram, and I'm going to get rid of this mess here. 3 dimension. Whoops, stylus. 3 dimensions. Right. There's no reason to talk about any of this stuff. The question we've been asked is not 2-dimensional. Don't look at the 2-dimensional diagram. Right? We're in 3 dimensions. We've been asked to compute a line integral. And so this tells me a couple of really useful things right off the bat. First of all, hey, check it out. Line integrals show up in these 2 theorems. Line integrals do not show up in this theorem. You can pretty much take it to the bank then that divergence isn't going to have anything to do with this question. Right? There's not going to be any 3-dimensional solid region. There's not going to be any triple integrals. Right? So just don't even bother thinking about any of that stuff over there. Does that make sense? Yeah. And now, just from a strategic point of view, and again, I know in addition to learning material, you also want to do well on the exams, and to do well on the exams, you want to cast a good impression to the grader, right? Obviously, right? And keeping in mind, what's the grader doing? The grader is not there to just check off, what's right and what's wrong. The grader is going to look at everything that you write. You're going to explain your ideas. The grader is going to digest everything that you've written and try to interpret from that, how much do I think this student gets it? Right? And so for your consideration, if the question is like this one about a line integral, and if a student really understood this diagram and really understood all the ideas around line integrals, divergence will never come up. Because there are no connections between line integrals and divergence in the way that we're doing things here. At different contexts there are, by the way, for whatever that's worth. But for our purposes here, divergence is not going to come up. Triple integrals are not going to come up. So for your consideration on a question like this, computing the divergence, that's not a good look. That's not helping to persuade the grader that you know what's going on. Right? So this is another nice contribution that the diagram gives you. The diagram tells you what to not write down on your paper to help you look good in front of the grader. Does that make sense? So don't, on a question like this, don't write down divergence, don't write down triple integral, don't write down a 3-dimensional region. None of that is relevant. Everybody see the strategy there? Okay, so that's the context from the diagram. Next thing we're going to do is we're going to compute the appropriate operator and think about the boundary and then think about what that tells us. So now, what do I mean by compute the appropriate operator? Okay, well, we are looking at we're in 3 dimensions, and we're looking at this line integral. We know that these are our 2 candidate theorems. If this is what I'm looking at, then I'm going to have a vector field that is my integrand. What does the diagram tell me to do? It's right there on the diagram. This vector field, it says right here, compute the curl of it. So go ahead, compute that curl. And by the way, the upshot, the benefit of that is if you get 0, then that means the fundamental theorem of line integrals is in play, because if you get 0, that means that your vector field is a gradient of some function, namely that it has an anti-gradient, and that's why the fundamental theorem of line integrals applies. Now again, the point here is that the foot in the door, the advice that led us to drawing this conclusion is to just do what the diagram tells you to do, right? We've got a vector field that's an integrand for a line integral. That's right there in the diagram, and the diagram is saying, do that. So the diagram will guide you toward good lines of reasoning. Let it. Right? Take the free good guidance. Likewise, analogously now, so in addition to I have a vector field, I also have a curve, right? And if I have a curve, for example, there's a curve. I can think about what the boundary points are, and so let's compute those boundary points. Those boundary points, see what you get. Well, there's a point there, that's your starting point. There's a point there as your ending point. And is your boundary 0? That's not from that picture that I drew there, right? That picture, it's pretty clear that no, the boundary consists of 2 points. On the other hand, what if your curve instead looked like this? So it starts and it ends at the same point. Arguably, it never really starts or ends at all. It doesn't really have a boundary, does it? And if your boundary is 0, notice that means that the curve in question is the boundary of a surface. And that surface is exactly what you need to be able to use Stokes' theorem. Everybody see that? So again, the diagram's explicit suggestion, right, is kind of what allows you, it takes you in the direction of a line of reasoning that allows you to decide whether or not, and yes, in the case of how I have it drawn here, whether or not Stokes' theorem works. So again, thank you, diagram. It's guiding us in all the right directions, right? It's making us ask the right questions here. So let's go back now to the actual question, and let's actually do this. Get that. There we go. Okay, so we have here. We've got a weird formula there. Let's compute the curl, I guess. Okay. Wow, that vector field, we're going to compute the curl of that vector field, and we get, okay, let's see here, I need the, y'all can follow along. We're going to take the y partial of that, and then we're going to subtract the z partial of that, which gives me 0. Then we're going to take the z partial of that, which is 2x, and then we're going to subtract the x partial of that, which is also 2x. So again, with the 0. And then lastly, the x partial of that, which is 2y, minus the y partial of that, which is 2y. And so again, with the 0. So I just computed the curl, got 0. Therefore, this is a gradient. Let me go back to the diagram. I took my vector field, I computed the curl, we got 0, Therefore, it is a gradient. It has an anti-gradient. That is the function that I would use right here in the fundamental theorem of line integrals. And so, yes, indeed, fundamental theorem of line integrals is an option. And probably a really good way to solve this problem. Everybody okay? Okay. And we'll go back to here just real quick. I know we're almost out of time. Let's entertain the question of the boundary. Okay, so I'm going to play the usual game. I'm going to plug in now, just because this happens to be a parametrized curve. Not all curves come parametrized. For different kinds of curves, you'll find the boundary in different ways. But in this case, I'm going to plug in t equals 0, and my starting point, x of 0 is t equals 0. Okay, so that's 0, comma 1, comma either the 0 is 1. Okay, now we're going to take the ending value of t. We're going to plug that in to get our endpoint, and it is, oh gosh, let's see here. Cosine of pi is minus 1, t is 1. Okay, so I get minus 1, comma, and you know what? I'm already done. We don't need to take this any further. Is there any chance that the starting point and ending point are the same point? They already have different coordinates. I don't need to compute the rest of it. They're different points. So my boundary is not 0. Going back to the diagram, and let's see here. Let me get rid of all of that. We just took our curve. We computed the boundary. It was not 0. That means there is no anti-boundary surface. That means Stokes' theorem is off the table. You can't use Stokes' theorem because your curve's not a boundary of anything, as is required. So we know our options now, right? So following the diagram, doing what the diagram says, we were asked to compute this integral, and the diagram has followed us, has led us by the hand to realize that we can use, that we can't. And so I advise that you try using this theorem. Okay, all right, I'm going to put up recordings for the rest of it. Okay, see y'all later. We'll do Chapter 4 tomorrow. And if we have any extra time, maybe we'll do some more of those examples. We'll see. Yes?
Is Chapter 4 going to be on the exam?
I don't remember what I decided on that. You got to look at the class schedule, whatever it says on the class schedule. I think it is. Yeah, so thankfully we at least have a weekend between when we're going to see that material and when the test is. If I don't test it on the exam, then I'm not testing it at all. So yeah. Okay, see ya.